Okay, this beta particle, why is this beta particle moving upwards? All right, so because this thing is negatively charged and that thing's positively charged, it's going to go up. And so because alpha particle is positively charged, and this is a negative plate down here, it's going to move towards that. And this doesn't go anywhere because it has no charge at all. Now, talk to me about this distance.
The beta is greater distance
Awesome. Why?
because the beta is smaller, so it's affected more by the positive.
It's a lot smaller, right? It's got a -1 charge, but it's a lot smaller, and this is a lot larger, and it's got a +2 charge. So even though it's better able to make the turn based off of its charge, it's so much larger. It's like a dump truck trying to make a corner faster than a Porsche. All right, how about the gas-filled radiation detector? How's that one work? What do you need? You drew a picture? Okay, so. Oops. Okay, so this electron that's negatively charged is going to move to the wire, and the argon that's positively charged is going to move to the can, because this is the positive charge of the battery and this is the negative charge of the battery. So the argon, the inside of this can is actually going to be negative, or feel negative to the argon, and this wire is going to be positive. So the electron's going to hit the wire, go into the wire, travel down the wire, go through the counter, get counted, and then end up back here, and I've got an argon with a plus charge waiting for it. So radiation, high energy. This needs to be high energy radiation because we're talking about argon, and argon doesn't want to lose any electrons. So then the electron ends up back at the argon, so the whole process can start over. All right. So let's do, we're standing at 25 meters from a radiation source. All right, so got some radiation source. Standing here, and at this distance, I'm receiving 120 millirem per hour. And I'm going to back up another 15 feet or 15 meters, and I want to know what this is. I'm also going to put 4 inches of lead in between me and it. So distance here is 25 meters, and then I got another 15 meters here. So my equation, I'm trying to find a radiation source, a value. So I'm going to put 120 millirem per hour in the numerator here. And then what's going to happen when I back up to the amount of radiation that I'm receiving? It's going to be less. So I'm going to put the bigger number in the numerator and the smaller number in the denominator. But this doesn't change by a linear fashion. It changes by the square. So I have to square the 15 and square the 25. And what do we get here? 20 times 15 squared divided by 25 squared. I got 43 millirem per hour. Great. So I said that this was gamma, and I also said that we're going to throw in 4 inches of lead. And the tent thickness for gamma is 2 inches of lead. So what do I do with my 43 number after I've slapped up the lead? Yeah, make it smaller. So I'm going to end up with 0.43 millirem per hour. All right, how about a definition for half-life?
Needed for half of the mass of radioactive material to decay.
Okay, that's good. And given a sample of cobalt-60, how long would it take to decay down to 60 grams? All right, so this half-life is 5.2 years. You could have found that on your periodic table on the backside. It says in the upper right-hand corner, it's abundance in the crust, and then one below that it says half-life of longest lived half isotope. And so for this one on my periodic table, it says 5.3, but yours is newer than mine, so that's fine. So we'll do this 2 different ways. I'm going to start off with 480 grams and 0 time. And then if I wait 5.2 years, I'm going to have 240 grams. And then if I wait 10.4 years, another 5.2, I'm going to have 120 grams. And if I wait to 15.6 years, I'll have 60 grams left. So it is exactly 3 half-lives. And then we'll do the calculation as well. And so that's time is equal to negative half-life divided by natural log of 2 times NO. And so that's 5.2 years, bless you, divided by natural log of 2 times 60 grams divided by 480 grams. 480 grams. And better land right on top of it. So we got negative 5.2 divided by natural log of 2, close parentheses, times natural log of 60 divided by 480. $15.6 years. Perfect. Okay. Sorry, that's a little low.